Hi, welcome back. In this video, we are going to finish our conversation on energy, work, and potential. In particular, this video deals with energy, electrostatic energy, that is. The idea is this: space, free space, and materials can harbor electrostatic energy based on the charge that they contain and how it's distributed, and that energy can be expended to do useful work. So think about if we had a spring and we compressed the spring and then we latched it. Now that spring is ready to do some useful work that we can use that energy. So that's the same idea. There are materials that are charged. Some we don't know how some materials we don't know how they became charged. If you're a religious person, then this might be part of your argument. But there are charged bodies, and the charge is distributed. It's like a latched spring, compressed spring, and we can release that energy in those charged bodies, the electrostatic energy. The stored energy, like the spring, is equal to the work required to assemble that charge distribution. So with the spring, the energy that the spring is storing is equal to the work that was required to compress the spring. So whoever made these charged bodies did some work, and now the energy that those charged bodies contain that can be released is equal to that work that is required to assemble the charged bodies. So now, in order to figure out how much energy these charged bodies have, we're going to imagine placing three charges, one by one, into an otherwise empty space, the beginning of the universe. We're going to place three charges. We're going to ask how much work is required to bring in these three charges. Then, that must be the energy that the system contains. Now, the work required to bring in the first charge, which I'll denote as W1, is 0. That's because this is the beginning of the universe, and this is there are no electric fields in this region. So I'm bringing in a charge from minus infinity into the universe. And by the way, practically, you might be rolling your eyes at my universe and my minus infinity, but remember that the electric field is proportional to 1 over r squared. So what we really mean is that we're bringing in the charge from some distance away where the electric field is negligible. The electric field strength drops off as 1 over r squared. So at some point, the electric field due to everything else is just negligible. Alright, so we bring in the first charge, and because there are no electric fields in the region, the work required to move that charge in is 0. W1 equals 0. Now, that charge in space, so I'll just draw my charge. Now I have one charge in my universe here, which is the blank screen. And now that is giving off an electric field. So now the work required to move in the second charge is non-zero because I have to move it against this electric field. And so we're going to call that W2, and that is, remember that work over charge is equal to potential. So we're going to say that W2 is Q2, the second charge that we moved in, we'll call this charge that's already there Q1, times, and we're going to use V2 comma 1. And so this is taken to mean the potential at position 2, maybe this is position 2, due to charge 1. So remember that this thing is given off an electric field, so there's a potential at this point due to this charge. And so that's related to the work, according to this. So again, this is position 2, here's position 2, here's position 1, due to charge 1. So I'm going to move in Q2 right here at this position. Now this is Q2. That's a bad drawing. Q2, right there. All right, now the work required to bring in the third charge is, we'll call that W3. So maybe we're going to place it right here. You can see how it depends on the distribution, right? That's going to be Q3 times V31, the position of 3, due the potential difference at position 3 due to charge 1, plus Q3 times V3 comma 2, the potential at point 3 due to charge Q2. So now we bring our third charge in like that. And so the total work to assemble those three things, I'm going to draw a subscript E for electric energy, is Q2 V2 comma 1, this guy, plus Q3 V3 comma 1 plus Q3 V3 comma 2, this guy, plus this guy, right? 0. Now, here's the trick. Now, this is a slick trick. Any term, let's say this term, is symmetric. And what I mean by that is that Q3 V3 comma 1, so that's Q3 times the potential at 3 due to 1. So that we've found that is Q1 over 4 pi epsilon 0 times the distance from 1 to 3. But because multiplication commutes and so on, and the distance of a vector from 1 to 3 is the same as the distance of a vector reversed, right, from 3 to 1, we can reverse the subscripts. And so by symmetric, I mean that Q3 times V3 comma 1 is equal to Q1 times V1 comma 3. So that is to say, the potential at position 3 due to charge 1 is the same as the potential at position 1 due to charge 3. So we could write the total work up here as Q1 V1 comma 2, reversing the subscripts, plus Q1 V1 comma 3 plus Q2 V2 comma 3, like that. And we can, or let's put it this way. Let's not set them equal. Let's say we could have written the work like this. Okay, so we have kind of two separate equations for the work. Now we could add the two equations, so we would have 2 times W and we can factor out Q1, we can factor out Q2, we can factor out Q3, like this. Hope you agree. Each term in parentheses is the total potential due to all charges except for that charge, for the charge at that point, right? So this is the potential, the total potential at point 1 due to 2 and 3, the other two charges. So we're going to just call this the potential at V. We're going to call that V1. And we're going to call this V2, and we're going to call this V3. So now, in general, we don't want to just talk about 3 charges. In general, we have the energy or the work required to assemble this is a summation from 1 to n, capital N, for number of charges, the ith charge, or the mth charge, I guess, times Vm, the potential due to all the other charges. This is the energy that it takes to assemble, and again, based on our original argument, that is the energy then that the system is storing once it's assembled. Now, as we've talked about a few times now, particularly with Coulomb's law, we're usually not interested in point charges, we're interested in continuous charge distributions. So we can apply a similar argument for continuous charge distributions, and what we see then is this thing. What we would have is 1/2 times the integral. So if we consider a continuous distribution as a bunch of small, infinitesimally thin points, then we would have 1/2 times the integral over the entire volume of the volume charge density times the voltage due to that infinitesimal point, right? And we integrate all those things up. And if we only had a surface, then this would be rho s ds, and if we had a line, rho l dl. But I'm using rho v as a catch-all for a volume. All right, now we're going to reach into our toolbox and we are going to recall some of our vector operations. This will be a fun little exercise. What I want to get is at the energy density. We'll take a look at what's called the energy density. So we're going to start here, and we're going to recall from Maxwell's equations, so that's one of our tools now. Maxwell's equations says the divergence of the electric flux density is equal to rho v, the volume charge distribution. So now I can make this substitution. Okay, by the way, the capital V is the voltage, the little v is the volume. Now I want you to recall a vector identity. It was actually, we argued that it was the product, it was related to the product rule for derivatives. That the divergence of a scalar times a vector is equal to the scalar of the divergence of the vector field plus the vector field times the gradient of the scalar field. The first times the derivative of the second plus the second times the derivative of the first, if you want to think of it like that. So if we take that and we rearrange it a little bit, we have this. This is our vector identity that we talked about previously. Now, we apply that to what we're dealing with here, right? So this becomes 1/2 times the volume integral of the divergence of v times d, like this, minus 1/2 the volume integral of d dot the gradient of the voltage, or the potential difference, like this. Now we're going to apply the divergence theorem. Divergence theorem relates a volume integral, which we have here, to a closed surface integral. Nice. So we're going to use the divergence theorem here on the left to make this like this. Okay, we're almost there. And I just want to make the argument now that this is 0. And the argument's going to go like this. Since our universe encompasses everything, effectively, we might as well consider R to go to infinity. And the surface integral, or so for this integral, so v varies at least 1 over r. We saw v, it was 1 over r, and it was 1 over r squared for the dipole. And D, or the electric field, varies at least as 1 over r squared for a point, or r cubed for the dipole. So the product of these two things varies at least as 1 over r cubed. And the surface area is related to r squared. So the dot product of those is 1 over r at least. So as r goes to infinity, this thing must be 0. And what we get, it's okay if you didn't follow that argument, what we get is that the total energy is negative 1/2 the volume integral of d dot gradient of v dv. And remember, lots of good things here, lots of good refreshers. Remember that the electric field is the negative of the gradient of the potential. So we can write this as 1/2 the integral over the volume of d dot e dv. That's nice. Now recall that d is the permittivity of free space times E. So now we have the integrand as epsilon 0, and E dot with itself is just the magnitude of E squared. We talked about vectors dotted with themselves a long time ago. It's just the magnitude squared. Now this looks like the sum of differential energy. So by that we mean, and I'm going to attempt to show a lowercase w. So this is now lowercase, where before we were using uppercase. So let's define lowercase w as the derivative of the big uppercase W versus volume. So this is how energy is concentrated in the volume. That is 1/2 epsilon 0 magnitude of E squared. You see that? So if we make that definition, and then we integrate it, of course we get the total energy. So we call this energy density, this guy, little w is the energy density. So take a charged body, and if you take a certain volume of that charged body, this will tell you how much energy you have there, and this is joules per cubic meter. All right, well, that's about all we have to say regarding energy, potential, and work. We've been talking a lot about free space, epsilon 0, the permittivity of free space. Now what we're going to do is have a major shift in focus in the course, and that is we're going to start to look at electrostatic fields in materials. So I'll see you then.